Jeff Derderian is a UMass Amherst ECE alumnus who is the VP of Product Program Leadership at Sonos Incorporated. In March 2021, he spoke to the current ECE seniors about his career at UMass Amherst, Draper Laboratories, and Sonos.
Well, Jeff, thank you so much for being available. It's been a joy to talk to you over the years and following your career. It's been marvelous. I want to go over that career a little bit.
And I did prepare some content to talk through it last night. So if you want, I can.
Fantastic. Yeah, I had your graduation year. I had that wrong. I thought it was 05, but it was
04. Yeah,
it was 04. Okay.
Yeah.
Okay. All right. Cool. So, yeah. Yeah. Do you want to show us some slides?
Sure.
All right.
I figured to organize the conversation a little bit, I threw some material together. I did this last night, so forgive.
Okay.
You know.
Yeah. Well, one of the cool things is that you've only been with 2 organizations. Sometimes people jump around every few years, but you've only been with 2.
Yeah. So the two have been the majority of my career. There's a little splattering of other things in there, which I can show you all. And
okay, and they weren't LinkedIn worthy.
No.
Hey, it's your prerogative.
I went back to a certain period in time in modernized.
That's
thinking.
good.
So, but I figured it was actually an interesting history lesson, because going back through old files and pictures and memories it was kind of fun poring over all that and throwing something together. So look, I'll throw it up there. However, I really don't want this to be me talking for the next period of time. So if we can get engaged here, I'll have a couple prompts. So be ready for me to ask some questions as well of the audience here. So
all right, and I want you to meet Shira Epstein as we go through here.
Okay, hi Shira.
That doesn't qualify.
Hi.
Okay.
Can you see this this initial slide here?
Yes.
Yeah. Okay, so what I had to clarify, class of 2004, set the record straight. I did stay on campus an extra year, so that might be what you're remembering.
That's it. And you were coy about it on LinkedIn, so I could have gone Inspire and looked at your transcript, but I didn't.
Yeah, you could have. So my LinkedIn is partially mine, it's partially Sonos's, because part of what I do now is talk to the press, so they have to kind of curate things as well.
Very good.
So today at Sonos, and we'll do this a little bit as well, I lead what's called the Product Program Leadership Department. So basically, for any program we run, any new product development we run, we have a group of leaders that we pull together to drive that program. That's a program manager, what we call a product creation leader, who's responsible for all of the product development functions, a product realization leader who's responsible for all of the operations functions, supply chain, manufacturing, etc. I have a product excellence department that's responsible for our processes, all of the continuous improvement initiatives we have ongoing, and a systems and tools team. So basically, that group all together drives a program along with our software team and our product management team. But before there, we're gonna go back in time, and it started at UMass in the radio astronomy department. And then from there went to Draper Laboratory. And I'm going to go a little deeper on each of these. Draper Laboratory, where I did some work with the Department of Defense and NASA. I view that as the first part of Draper. The second part of Draper was a complete focus on ultra miniature systems, which I'll touch upon a little bit. From there, kind of overlapping between that end of Draper time period, I did some medical devices work as a consultant, and then moved to Sonos making smart speakers. And you might look at this and say, quite the change from Department of Defense to smart speakers along the way. But I think you'll come to find that under the hood, they're not all that different. which is the interesting part. But let's start with the closest to home for all of you, which is the radio astronomy department. And this is a place that I started working as an intern, I'd say somewhere late sophomore year. And it was just an amazing way to learn about board design, learn about how to procure your own parts, build your own boards, test it. It was such a small shop that you had to do everything. You had to wear your hat, wear every hat possible when it comes to bringing up systems. And although the systems, each system in and of itself, each board in and of itself, I wasn't exposed to the full end to end. I got this crash course in all things double E, right? So doing that at the same time as finishing up my studies was just an amazing experience. Here are two boards that I designed there, which were again just a great experience. The one on the left here was a mixed mode PCB. So we actually stacked the two different materials, one that was great for RF properties, the other were low cost and good for your standard FR4 digital designs. But we mixed them together in order to do this single board go into a backplane. And the one on the right is a processing unit that would receive a bunch of information and process that through that Xilinx FPGA over on the right. Again, we're going back a ways, so I'll gloss over the details, but suffice it to say, great experience doing this. And these were obviously assembled in a shop, but early prototypes of this I would have assembled by hand as we were building up the individual circuits and tuning them. So just a tremendous experience. This work was targeted towards something that I never saw come to life while I was there, but I was happy to see that it did end up coming to life. At the time, we called it the LMT, but it turned into the Alfonso Serrano Large Millimeter Telescope, which at the time, I don't know if this still holds true, but I believe it was one of the largest scientific ventures between Mexico and the United States that had existed. So really a tremendous program. From there, and jump in if there's any questions, feel free. From there, as I mentioned, I then went over to Draper Laboratory, which is in Cambridge. And this is it's unique because it's actually a not-for-profit research lab. So everything that happens, all the revenue that gets generated gets funneled back into independent research and development, which is amazing. So it allows that organization to do a tremendous amount of IRAD, independent research and development, in order to build up new technologies, new capabilities, fund university research in many examples, and at the same time deliver on very important missions that serve the nation's interests, right? And it really covers a very wide range, anything from, again, DoD, biomedical, space exploration, so on and so forth. And one of the claims, claim to fame for Draper was they were involved in every manned mission to space, and really, Doc Draper was the father of modern initial guidance, right? So really a tremendous place. I spent about 9 years there, and I cut it into two segments. When I got there, I started as a digital designer working in like many, about 50% of the company at the time was focused on the Trident missile system. They worked on the guidance system, making sure that this missile went where it was supposed to go. So like many people there, started out there, and the image on the left here, this kind of cross-sectional view of a circuit board, is meant to really remind myself of what I was doing. So at first I was really deep into signal integrity design. And I don't know if you all have heard of that, but if you've done printed circuit board design, you have to ensure that you follow proper rules to design those circuits so they operate properly. Have we talked about any SI type work yet in the professor?
Probably not. I mean, not in this course.
Got it. So let me I'll give like two seconds on it then. So basically, on paper, you can design a circuit, and then when you lay it out and have it operate in the real world, it could operate totally differently. And it could operate differently at different temperature extremes. It could operate differently in a variety of environmental fashions. And just the way you laid it out could create noise that will leak into other areas of your circuit. So signal integrity analysis is critical, and understanding the fundamentals of that. So I get to Draper. There's this expert there. He's 20 years, 30 years experience, wrote the book on SI. I'm excited. I'm going to learn from this person. And it was me and him. We were going to do all the SI work for this large backplane. And about a month, maybe 2 months in, he leaves. So then it was me. So he left me with a bunch of his, research, a couple books, and I started reading about SI. And I became one of the experts on this topic for what I was doing there. And I mention this because if there's something you want to learn about, just start reading about it and get your hands dirty. And that's always going to work. Learn, experiment. And B, learn about SI if you want to actually build circuit boards, because it's going to be critical. And you're going to build a board, it's not going to work quite right. And you might get it to work on one or two, but if you have to make a million of them, you're going to definitely want to do some SI work to make sure you get that right. What was also interesting about this is, and I bring this to the image on the right-hand side, was some of the work I did was for NASA's Crew Launch Vehicle in fault-tolerant computer processing. And what I was doing, again, I was applying that SI work into this domain in order to design, proper cable harnesses, and also design rad hard systems. So anything that goes up into space is going to get exposed to radiation. And what you'll also come to find is all these things like capacitors, in the real world, aren't just capacitors. They're actually capacitors, inductors, and resistors. And when they get hit with radiation, they short out. So you have to be able to calculate how is that going to occur? What's going to happen? How do you hold up the system so that when that occurs, the whole thing doesn't reset? So again, one more plug back to SI work as being a great foundation. So this was about my first maybe year and a half, 2 years at Draper. And then I moved into an area that, sorry, I'm gonna click over here, was basically centered all around a block diagram that looks something like this. And you're going to have some sort of electronics module that we wanted to miniaturize as small as possible. So take something that might be, I don't know, fit on something about yay big, and shrink it to the size of a quarter, right? So that you can package something down incredibly dense. But the issue here is that's this electronics module. You always have to interact with the real world in some way, shape, or form. So then you would put that module onto some sort of an interposer or interconnect module. So you can then link it to a battery or an antenna or some sort of button or some sensors. So this general block diagram was the heart of things. And to show you a little bit of what that could have looked like is you might start with something like this. So on the left-hand side here, does anyone know what you're looking at? Any clue on what that is? On that bottom left, it's like, it doesn't quite look like a component that you're used to seeing. Any guesses what that is? This is the interactive portion of the discussion. So we'll see if anyone's awake. Any thoughts? Any guesses?
Not a clue.
Not a clue. So what you're looking at is the bare silicon that exists inside of the ICs. So normally you're used to seeing the little black rectangles that are the ICs. Well, that's just plastic that's been molded over, plastic or ceramics is molded over the bare die. So this is what's called bare die. So internal to that is this. And what you'll come to find is that packaging is wasted volume, right? So if you can get rid of that packaging and instead connect directly to the bare die, you can make a much smaller circuit. And at Draper, they had a process to do this. Either we'd procure a wafer of bare die, or we'd actually take the packaged part and we'd thin it down and extract the bare die from a particular part and assemble it together on a Kapton substrate. And then you build that up and you build around that circuit at a very small scale. So you all are doing some PCB design. What kind of trace and space rules are you working with right now? Like trace widths and spacing between traces to again, interactive portion here. Anybody know some common rules for standard PCB technology?
5 mil minimum usually for us.
There we go. 5 mil trace space. And that's about right. So with this, we could do 1 mil trace in space. Everything compressed way down. Not only 1 mil trace in space, but every layer had its own via structure. That's called blind and buried vias. So now we had the ability to route directly to wherever we wanted to go. And back to the signal integrity for a moment here. When you get on this scale, those properties of SI, because you're so small now, transmission line effects kind of go out the window. So you can now eliminate components that you don't need anymore. Again, furthering the ultimate reduction in size. And then eventually you wrap this, up in some sort of board that again connects to the real world. So just a quick example here of what one system, might look like. Here's another example. Again, a dime there for some scale. This is some work that I did for what we call the URAD, University Research with Berkeley. And the question is, again, what the heck is this for? Any guesses what this was used for? Any ideas?
Can you show us the picture, like
Yeah.
before the bulb?
I don't know if I can go back without it yelling. I think if I click again, it's going to go to the next. It's going to go to the next slide, which will give it away. I think no one would ever guess what this is for, so I'm going to keep going.
I'll guess anemometer. No.
This is a little backpack for a locus. And the university was trying to do research to see if you could steer locusts through basically overloading their infrared receivers that they use to steer and fly. So the way a locust flies, it's got 3 little ocelli that sit on the top of their head that act as a UV detector. And when it looks on the horizon, it sees light and dark, and it can tell what the horizon is. So if instead we replace that with our own light, we could then flash some light this way and make it steer one way or another. So at the time, the university was doing tethered experiments because they had no way to build a small enough, light enough, self-powered backpack that they could put onto one of these insects. So I said, well, I can do that, and made this little circuit board that folds up on itself. So they mounted it on there and they ran flight tests. And this little black chip here is actually the battery. So that's a surface mount battery that's typically used for, if your computer like shuts down and you want to hold up the clock circuit or something like that. So it's meant to give very, very, very small amounts of energy, but work perfect for this example. Okay, so then again, overlapping with Draper here, I was doing some consulting. Dipole Engineering is actually my father's consulting company, and it's just him. And he's an analog designer, like deep analog designer, and like works on the very front end, converts it to an electrical signal, and someone else takes over. So he wanted someone else to take over. So I then was the other half of that, bringing it into the digital system, writing code, adding wireless capabilities for a couple projects. And I threw a couple out here as some interesting examples. So the one on the right here was a radiation sensor for basically when you do cancer surgeries, you'll put tumor markers that are little radiation, points, and you use a probe like this to zero in on where you have to operate. And the issue was it was wired. So they wanted to make this probe wireless. And again, I said, well, if you do the front end, I'll do the back end. So I made a small board and stuffed it in there with, a wireless transmitter and connected it up to this thing and got that going, which was, again, super fun and interesting and a departure from the stuff I was doing at Draper at the time. On the left here is actually an image of what's called a dosimeter, which is a way to detect radiation. And that allowed you to throw to a display what kind of radiation is present in any environment or wherever you are. You can use for a variety of different reasons. So a little bit of this, there's other projects in here as well, but I show this because it was really interesting to try and, as I was going very deep on Draper in a variety of areas, to kind of stay, a little bit broader. My mission has always been to stay as broad as possible and continue to go deep in a variety of areas so I can be effective as a leader. So some examples of that. And then that brought me to Sonos. So at the time, I was down actually in Northern Virginia for Draper. I had opened a new lab that was a business development lab down in that area. And I was looking to get back into Massachusetts, and then found Sonos, which was basically the second half of my career. And the departure from, again, at Draper, making 1 to 10 units of something that was so custom and specialized to now making millions of units was quite the departure, quite the learning curve, and incredibly fun. But under the hood, like I mentioned in the beginning, it's the same stuff. That same block diagram that I showed before applies. Maybe we've got now a power supply instead of a battery. We've got transducers as speakers instead of other sensors as inputs. But it's the same stuff. Everything applies in what you do. So when I started at Sonos, my first project was something called the signature detail. And this was a fascinating way to get introduced to Sonos, because it was, what we have zoomed in here is what the sig detail was. It's basically the controls. How do you control the speaker? And you might think that, oh, that's pretty straightforward. It's pretty simple. At the time we had some mechanical buttons. They wanted to move over to some capacitive touch sensing. And one thing that you'll come to find is that companies that really care about their products is that even something as simple as I want some capacitive touch pads to control my speaker is incredibly challenging. And that's because when you're at a company that cares about the product so much that you scrutinize every detail, doing this means we had to do it right. And at the time when I started this, I said, well, I think we've all experienced capacitive touch that's either really great, like your iPhone, it's really great, that's fantastic. And then you've experienced cap touch that's not so great. And in the middle, there was no room for anything else. So I said, if we're going to do this, it's got to be really great. It can't be in your car when you tap it and you have to tap it a couple times because the touch sensor isn't sensitive enough. When it has to have the right feedback, have to have the right sound. Everything has to be incredibly responsive. How do you deliver that? And what was fascinating is now the timeline here was the company actually didn't want CapSense. It was a small group of people that wanted to push this new technology forward, but the program was marching along. I said, well, if we don't make it by this date, it's gone. We're going to cut it. And I said, well, we can hit that. So we worked hard. And again, it was an incredible crash course in Sonos because it's as cross-functional as a program comes. It was software, it was hardware, it was new R&D, it was industrial design, user experience, it was audio engineering. We had to design the sound, that the little beep and bloop that it makes. We had to master that sound with audio engineers, the full range. So a great introduction to the company and to the people, and really the care and feeding that goes into product development. That then became our new interface. That became, it's still on our products today, this interface. From there, I started working on this product, which is the Sonos Move. And this is our first battery operated product. And this started out actually with a different internal code name. We have code names for all our product development, but we actually started this many years before we launched it. And we put a good amount of R&D into this, and then we said, you know what, we need to hit pause, because the technology to deliver what we wanted to deliver what we call the right product, it wasn't quite there yet, and we needed a little more time for things to mature in order to actually launch the product we wanted to launch, which was a Bluetooth speaker. A Sonos speaker, which is Wi-Fi whole home audio, that had Bluetooth as well. And how do we blend the two in a way that's a Sonos experience and is seamless and is premium? And just wasn't ready yet. So instead, I moved on to lead this product, which is the Sonos Beam, which became the #1 soundbar in the world. For a couple of years now. I think it may have recently been usurped by the Arc, which we launched just about a year and a half ago. But this was just an amazing experience, getting to work on a product after working at Draper on things that I couldn't and still can't talk to anybody about. Work on a product that I could actually give to people and hear about the joy that it brings to their lives when it comes to filling their homes with music, which is what we do. And I've got some under the hood images of this one that I thought could be fun to look at. Mm-hmm. So the first question, though, back to the interactive portion, so no one's falling asleep on me here. How many boards do you think are inside this soundbar? How many printed circuit boards, or you can guess circuit boards, antennas, flex circuits? Any guesses? What's under the hood?
32.
8.
We've got a 32 and an 8. My son guessed 117 this morning, so I told him he was wrong. Well, I heard a 1. Think a 1 in there?
Yep. Okay,
so under the hood here, here's an exploded view of what this looks like. And I've got some actual image. This is actually a rendering. This is an ID rendering, which is why everything's so beautiful and spaced and perfect. But six boards. So we've got a radio board up here, which is a dual band, dual concurrent radio. We've got a CPU sitting over here. Over here is a power supply and amplifiers. Up top is what we call the SCI board, which is all the signals, the cap sense, the sensors, the microphones. This little guy in the front here is an IR receiver, and then along the back is a button board to allow you to join the system. Connecting all these are 3 FPCs, flat printed circuits, and so flex cables basically, and 4 antennas that are dual. So 2.4 and 5 gigahertz, 2 on this board itself and 2 remote, which I've got some images of. A Bluetooth low energy antenna up on the top of this board here, 4 woofers, 3 passive radiators, a tweeter, 5 microphones, and a partridge and a pear tree. And that's just the guts of the active components in here. But just an example of, when you build a system like this, there's a lot of engineering that goes into it. And you have to be thinking about not just your component, but how does your component affect everything else, right? And if we moved a screw, that could change the whole product, because the antennas were tuned with the screw in this one particular position. So everyone had to work together. Everyone had to collaborate. Everyone had to communicate. And we were doing this globally, right? The team was in Boston. It was in Santa Barbara. It was in Seattle. It was in Shanghai. It was in Shenzhen. It was in Hilversum. And we've been using Zoom for about a year, so we were used to Zoom. Every meeting has been a Zoom meeting almost the entire time I've been at Sonos, because you've got to collaborate constantly. You have to communicate. You have to make a plan, communicate a plan, and then if you have to adjust, you communicate the adjustment and you keep on reacting to that. And CDR, I was seeing Professor Hollett talking about CDR. We have CDR. All the same stuff that you're learning right now in your senior design projects, will be applicable when you get a product in the real world. And lean on that. In this course, I've got my two favorite professors right here on here because of what I learned from the senior design project with Professor Souls, and many of Professor Hollett's courses were always my favorite. So some actual images that aren't design renderings, so you can see a little bit of what's going on in there. Without the hood on, the board's kind of assembled in there. This is actually the first prototype we built, and the system afterwards looked very different. The other thing you'll find is when you actually build something, you're going to have to adjust that, because no matter how well you planned it, it's going to be wrong. And so build fast, learn from it, and then build again. Have a test plan, execute that test plan, refine it, and build again. And that should be all part of your plans, right? Top view, give you a little bit better view of what's going on in here. This one's quite messy looking because, again, it was pretty early, but you can really see under the hood here, again, the radio board here, CPU. These rectangles are the magnets for the transducers. Everything you see here was custom designed by my team, with the exception of the screws. We buy the screws off the shelf, but everything else was a custom piece that was designed in-house. Clicking a little bit more, again, this is that IR receiver board out in the front. We've got this button board in the back, the two remote antennas that you see over on the right-hand side here. This is in a as we're assembling it flow. The radio board getting assembled. You'll see some of those flex circuits getting ready to go. That CPU getting snapped in there. Again, just some overhead shots of the power supply. This is that SCI board with cap sense. You need to make sure you have no air pockets, real intimate content with the surface above it, because air as a dielectric of one is gonna really impede your capacitive sensing, versus plastic like this is higher. And then it turns out to do something like this, and you get to talk about it with the press and sell it and hear the reviews, and again bring joy to people's lives. So that's a bit about the Sonos journey, and this is just kind of a snapshot of the various products that I've had the pleasure of working on since being at Sonos. So again, this was the tour that led me to my current place here, starting again all with where you are right now, and that learning from that last year, and the realization that you can really apply everything you're doing right now to the real world. It was a good one. So questions. Now it's what I had to share as a seed here, and we can go from there.
That's great. Thank you so much, Jeff. Why don't you, I think you can turn the screen sharing off. Yeah, great. Yeah, I've got a bunch of questions. I'm going to give you 3 questions and you pick one.
Okay.
How's that? How often do other companies try to steal you? How can a woofer be small? That sounds counterintuitive. Yeah. And are your factories, are they owned by Sonos?
Great questions. I'm happy to answer them all, but if you want me to
really? Okay, all right. All right.
I'm here. Let's do it. So reverse order, because I don't remember the first one still, but the factories are not owned by Sonos.
Okay.
So we have what's called a CM model, which is a contract manufacturer. So we have different CMs that we partner with, and we have offices in China and Malaysia where we do our manufacturing. And those the people in those offices are responsible for working with those CMs, as well as the teams in the US. We always fly over to China, get on the ground there to bring up a new manufacturing line. But they're responsible for the actual manufacturing line. So we bring it up, we qualify it, and then they run it. And then of course you have to maintain that line. So once you launch a product, you'll find that if one component goes obsolete, that whole product line goes down. So you have to always be what's called sustaining that line. So we have a whole department that's focused on sustaining and making sure we can source components and work on bringing up alternative second source parts. So no, we don't own that, but we do manufacture with 2 different CMs, both in China and Malaysia. And then the woofer question, how can a woofer be small? So a woofer can be small, but it's always about compromises. So when you're trying to produce great sound out of a product, you need, let's talk about Beam, you need for a sound bar. So when it comes to great sound from a sound bar, we think about 3 things. It's in this order. Number 1 is center channel clarity. It has to be really crisp, because most people buy a sound bar because they want to be able to hear what people are saying, and TVs aren't great for that. The dialogue and intelligibility on televisions is quite poor. So you need a really crisp center. Second is spaciousness. You want the sound to be as wide as possible. You want it to be bouncing around the room. You want to be reflecting rear channels. You want it to be beyond the edges of your screen. Because oftentimes that's what is trying to be conveyed to you is not always visible on the screen, coming in from off screen, coming across and panning. You want to be able to tell that story as the producer intended it to be told. So that's second. You do that with arraying. So that's why in many soundbars, you'll see a whole bunch of different transducers working together to steer sound as broad. And that's all in the signal processing that happens under the hood. And third is bass. You need to be able to feel, those explosions, the deep, bass that happens in music. And to get bass, you need to move air. And that's where the woofer question comes in. So you'll see you can either move air by having big woofers, but as a woofer gets larger, it's going to not work as well for the higher frequencies. And we also, for a soundbar, you've got a space constraint. It's got to fit in and around the TV. So you can do that instead of with fewer larger woofers, you can do with many smaller woofers, and what's called either a ported system, or what I showed there was a passive radiator. So you've got a bunch of other plates that will move air, and they're tuned to resonate at a particular frequency. So as the box gets under pressure and all the air is moving because of the woofers, those PRs, passive radiators, will start radiating, and in the low frequencies push more air volume.
Very nice.
It's all of this. The other thing you can do is, again, you're moving air. You can have a cone that has more throw, so it'll move physically more millimeters as opposed to a larger diameter with smaller millimeters. And that all comes down to the power of the system, how much power supply, how much the BL of the magnet, how much force you can drive that with. So that all links all the way back up to the power supply. And again, everything affects everything. The more you pump into that, the hotter the system gets. And then you've got thermal issues, right? So it's all interconnected. So they're all trade-offs. It's all trade-offs with one another. And I forget your first question, but I remember.
How often do other companies try to steal you away?
Oh, me personally?
Yeah.
Constantly. Not to sound conceited, but yeah, you get emails every day.
Okay, you just ignore them?
I just ignore them. I don't want to go there. I love what I'm doing. Yeah.
Nice.
I have a question. So we're talking about, system specifications and student projects and how they come up with a series of tests to find out if they've accomplished their system specifications. So obviously there's a beginning stage of simulations, as the prototype gets built, and then maybe there's an initial manufacturing run. How do you characterize, the performance of these devices, and maybe do some testing and then statistical analysis before you go into like the full scale production?
Great question. So our development process, let me give a little overview. So it's pretty well established. The way we do it's very methodical. So when we start any new idea, any new program, we have a phase that we call incubation, and that's where we put our ideas to incubate and see if at the end of that incubation there's something that's going to hatch or not. Right. So we take an initial idea, and it always starts with what we call the customer requirements. Define the product from the customer's experience. Because without that high level requirement, you don't know how to then develop a system, right? So we want, again, we'll use Beam. We want a sound bar. People love the play bar, but we've done research and we found that it doesn't fit everywhere people want to put a sound bar. We need something that's smaller. We also see trends that say that in certain markets, urban environments, there's just not enough space. We also see trends that, hey, people want speakers in their bedrooms or in areas that they don't want to put a super expensive soundbar, and they want to put something smaller. So it starts with the requirements. Have good customer requirements. From that, derive your system requirements. Okay, we want this to sound good. Okay, thank you, customer requirement. It's more complicated than that, of course, but we then derive that into, okay, what's the sound experience targets? And like I described, central channel clarity, what's the priority stack? Is it center channel or is it spaciousness? Is it bass? They're all trade-offs. They're all trade-offs with one another. Define all that. And then we go into what's called the creation phase, in which we architect the system. We derive the requirements. We start architecting simultaneously multiple designs, multiple acoustic architectures, and usually one, maybe two electrical architectures, because all of those have to be in tension with one another as you make these hard trade-offs, right? And you align on what we hypothesize to be the right system architecture. Through that, you're doing engineering ups. You're building subsystems. You're building something that emulates the system to do antenna testing, something that emulates the system to do thermal testing, something that emulates the sound, right? So every single product we make has the transducers in an MDF box that has the right acoustic volume, and it's plugged into, you know, some electronics on the side so we can see and test out different hypotheses. Simulation, we simulate everything. We simulate thermals, we simulate finite element analysis for the mechanical, we find the vibration modes in the system to try and predict where stresses might occur. We run signal integrity analysis, we run, you know, all sorts of analyses to ensure antenna simulation, everything under the sun, simulate as much as possible. And then we do all that in the creation phase to say, we think we have a system. Now we're going to go into what's called the prototyping phase. We've already prototyped on the engineering mock-up scale, but the difference now is we're saying we believe we have the right architecture. We want to build it at scale. We want to build it all together now and start learning. And you start with what we call our P1s. This is our machined plastic, 3D printed, you know, maybe we've tooled up one particular plastic piece that's challenging. Oftentimes our grills are quite challenging. So we might tool that up. We put that together. We build 10 of them. And we do that by hand. We fly the China team over. We fly our CM over so they can observe and take notes. And we build it by hand. And we're in there, and it is so fun. You're in there for a week and a half, working late, finding issues, seeing this thing come to life for the first time. There's no feeling like it. And then you hold it in your hands. It's like you're, you know, another child, right? I've got two kids. It's like, it's not as good, but it's pretty close. It's pretty close. And you've got this, and you can listen to it, and it's amazing. And then you start testing it. You've got a test plan in place. Our hardware verification team has a long litany of tests to go through, and you find all the bugs. You log all the bugs. We have something called Jira, which is our bug tracking system. Everything goes in Jira, and we start working all the bugs, finding solutions for revision 2. And we do oftentimes the second one of those because we want to make sure before we hit go on the tooling purchases. Tooled plastic parts cost a lot of money, like millions of dollars. Before we say, yes, let's spend, you know, $1 million on tools, we want to make sure the system's good. So again, we simulate again, we test again, we correlate our thermal testing with the simulation to improve that, to get better predictability. And then we say, okay, we think we're ready. We can't do anymore. We can't learn anymore before we hit go and take that leap and build in China. So we hit go, make the tooled parts, and we have your first build on the line in China. And oftentimes it might be a proto line, so not the full manufacturing line, but you go there and you learn even more because now it's somebody else building it. And now you're building 200 units. and you're running those through hardware verification testing, and you learn all of the issues that come from that, hardware and software, packaging, you just everything, right? All the issues that come from it. And we usually do 2 cycles of that, and we have our CDR after our second prototype build in China. And we say, okay, this is it, pencils down. We're not doing anything else. We're going into what's called EVT, your engineering verification test build. Now we're making production tools. This is it. We can't change anything else. We're going to start qualifying second source parts. And then we say, okay, we're ready for this. And we go into EVT, and then we find more bugs that we have to solve. And it's always the case. Best intentions, but it's always, risk reward. We've got this bug. We think we can solve it. We think we've got to fix. Do we hold the whole product up, or do we miss our GA date, or do we keep going? These are the things that are constantly in play. You go to your EVT and you build again. Now you're building 1,000 units. You build 1,000 units, and you start doing what's called alpha testing, which is all these units start showing up internal to Sonos at our various houses, and we start putting it through real world testing, because nothing replaces, no matter how good your verification plan is, nothing replaces the fact that when it gets to hit 1 million households, someone's going to do something crazy with it that you never thought of. I've seen, sound bars on top of refrigerators. I've seen, sound bars on top of pianos bolted to a tree outside. You never think of, but you research and you talk to your customers and you go to their homes and you ask them, how do you use it? Because we're not the customer. You're making the product, but you're not the customer. You can never be the customer. You're too close to it. You got to hear, you got to talk to people. At DVT is when you've got your manufacturing line. Sometimes you need a second line. You bring up a second line because you have to produce, like with Beam, units per hour is the metric. How many units per hour do you make? So every hour you're spitting out 200 units. Sometimes you need 2 manufacturing lines to do that. So you build a second one. You build copy tools. Those tools worked great. Now we need more of them to keep up with that UPH. So how are we going to do that? We build them, we qualify them again, you test them again. Now you're at DVT. Okay, it's time for beta testing. Now we're testing not internal, we're testing external. Now it's going to go into our beta pool, not internal to Sonos, and they're going to find all sorts of other bugs because we're used to all the bugs and we know how to get around all the nuances. But now it's different TVs it's going to get plugged into, and now we're dealing with interoperability issues. And then eventually you think you're ready, and the ultimate test is when you ship it. And you're not done until you ship it and you see the reviews and you see if it sells and see if people love it or they hate it. And that's when you really know. So you prepare as best as possible. You test, you simulate, you learn, you adapt, and you do it again. And again, you have a plan, and you're always prepared for. You're always attempt to be prepared for when things go wrong, which is called risk management. What are all the things that could go wrong? Those are your risks. And when they happen, they're issues. And you always want to be making sure that you only when you're doing product development, you only stumble upon new issues. Because if it's a lesson you've already learned on another product development, that's a problem, right? So you always want to learn from that, adapt, and don't make that same mistake again. So I don't know, that's a long-winded answer, but that's the flow. That's the way it happens.
It's fantastic.
How do you make sure that Sonos speakers are backward compatible so that in 15 years it still works with modern devices?
Yeah, that's a great question, and it's man. So when Sonos launched, the iPhone didn't exist, right? So there was no iPhone when Sonos first came out. So and I wasn't there at the time, but the team had to adapt from no iPhone to world of iPhone and controller and cloud-based connectivity and everything, and operate in the same system. So fortunately, though the architecture of the system in every Sonos speaker is basically an ARM processor, a Wi-Fi radio, and tons of signal processing under the hood, and then a lot of memory. So we at the time would design it for more than we would think, so that over time, as we add features, add capability, add, you know, everything under the hood, you have room to grow. So you never want to max out your processing capability or your memory allocation if you want that product to live over time. Now, the question is, how much do you put in? Because every bit of extra processing, every bit of extra memory is added cost to the product, which means added cost to the customer. So how do you find the right balance of future-proofing versus versus cost? And that's what the trade-off becomes. But our software team is amazing, right? So they're always looking for more efficient ways to do things with more. We've only had to say we're no longer going to push new features to our very oldest products that are over 15 years old. But everything else we're still supporting, which is frankly unheard of in anything that has a computer in it these days.
Yeah, that's great. Can you say a word about C, C++, and Verilog, VHDL? Do you folks get involved in
Yep.
both the MCU world and the FPGA world?
Yeah, both. So we're typically so there's many different layers to the stack, but the heart of everything is an ARM processor, and our latest products have quad core ARMs, and then they typically have like M0, M4, something under the hood as well to do more real-time operating system type stuff. So it's always a mix, right? So our software team writes the drivers at the lowest level, all the way up, all the way up to the highest level of running Linux, and then writing code on top of Linux to run internal to the product. So everything up and down the stack there from a C perspective. Then there's certain things that you need really specialized code for, which is where we'll put a CPLD, an FPGA, something like that down. It's less frequent just because we always want to drive things into the fewest number of components possible. So if we could have done that operation on the SoC that had the ARM, the ARM processor, we would have. But in this example, a couple times we need to put a small FPGA to do a really specialized operation. But then the goal is always to design that out in this application, right? For Sonos, just because we'd rather eliminate that silicon and push it.
And what language for that FPGA?
VHDL typically.
And can you tell us any vendors for the ARM or the FPGA?
Well, we look for let's see. So what's interesting you'll find is another tension that exists here. You want to use reuse components as much as possible, but if you only use one vendor, now you have what's called a single source. So if you lose supply or that vendor goes down, you're in trouble. So you want to be able to dual source things, right? So as an example, a lot of components might come from a particular factory. If that factory has a fire, you're done, right? Your whole product line goes down. You got to move all your parts over to something else. So you want to diversify. So for SoCs, we've got a couple different vendors in the mix. We work with, and we've worked with a variety of vendors over time. Things like NXP, AM Logic, MediaTek. These are all companies that make SoCs, and you'll find those all in our products in one way, shape, or form, depending on the product. What we try to do is create what's called a platform, right? You want to build a computing platform that you can reuse on a certain class of products. This computing platform can be used on soundbars, or this one can be used on portable products, and then reuse that. Now, it's not reuse in the sense of we're going to use this exact board, because in doing that, you've then constrained the system, because every product is unique in its form. So you're always going to relay that out, but you might use common blocks so that you can, okay, I've worked out the signal integrity of this computing platform to the memory. I'm going to grab that chunk and drop it into this new design because I've already worked that out, and that works really well, as an example.
Right, cool. Any questions from students?
Yeah, I actually had one question. Yeah, I was just had a question about for like your competition. So for Sonos, like when you're making like your soundbar, for example, uh, do you think, can you like kind of think of something that sticks out as what may put you on edge over like Bose or some other speaker company?
Sure, sure. Let's see. So what makes it a compelling product? Why would somebody want this over everything else that's out there? A couple things. So one of the foundational elements of the company is that Sonos is a system. So when you buy a product, it works with every other product. And that's fairly unique. A lot of other competitors are either just starting into that, or maybe they've got a couple variants of their system. So certain classes of products work together, and then others you have to go to a different system for. So what's great is that you can always add on. You can start with just the one soundbar, and then, you know what, I want more bass, so you add a sub. I want surround, you add surrounds, and you can just build it over time. And then move things around. So that systemness is one element that I think is fairly unique. I think, again, other companies do some of that, but we've been doing it since the beginning. The second thing is the attention to detail. And this is like the thing that when you look at the product, when you look at something, you just know that there's something premium about it. That is because of all of the attention to detail that went into designing that product. And it's caring about every little bit along the way, starting with, the experience of the website. How do you show up there? When you purchase the product and it shows up in your home and you unwrap the box, how is the product presented to you? Is it easy to get to? And I talk about it as you either climbing that curve of delight from that first step, or you're going down. And as soon as you start going down, it's going to be harder to climb back up. So every step along the way has to be very carefully considered and very intentionally delivered. And a lot of this becomes subconscious. So if you look at Beam, you'll see this shape on the top of the product that's a racetrack. That racetrack shape, if you flip it over, is continued into the foot that hides the screws. So you see no screws on it. You'll also notice that there's no seam in the fabric. We actually wove the fabric for the grill like you weave a sock on a giant loom machine. So we can make a single piece of fabric, cut it, wrap it, so there's no seam. Well, why would you do that? Other company, you just put a seam on it, because we care so much about every little detail. That same racetrack shape you'll find carried through in the power cord. The shape of the cord is that same racetrack shape. The HDMI cable has the same racetrack shape. These are little details you might say, like, what does it matter? Just get an off-the-shelf HDMI cable, off-the-shelf power cable. But it's the extra step that subconsciously you're going to look at that and you're going to feel like you got the value. The other thing is when you turn it on, the setup flow is clean, it's simple. And then when you listen to it, we always want you to get more sound than you would expect for the product. So this product is slim, it fits, it's small, and it should deliver surprising sound for its size. So the combination of all those pieces together, and it's really through the tensions that I described before. The acoustics team always wants bigger volume. The design team always wants it smaller. And through that tension, you do something and you create something that you didn't know you could by just compromising, right? Most soundbars are extruded rectangles. None of our soundbars are extruded rectangles, because you want something that looks good and fits in the environment and feels like a piece of furniture, not a piece of technology, right? And it's all of that together, right? So it's every step along the way, you care and you scrutinize every detail until you get it right. And if it's not right, you don't ship it, and that's it. I guess that's my answer to that one.
Okay,
Jonah,
cool.
you have a
Thank
question?
Hi, can you guys hear me?
Yeah.
Yes.
All right. Well, thank you for coming to talk today, Jeff. And I was wondering, so if you have a Sonos system with multiple speakers and maybe they're in different rooms or something, do they need to be wired together, or is there some sort of like time synchronization that can go into getting the audio lined up across different devices?
Yeah, it's all great question. Yeah, that is the beauty of the system, is that it's wireless. So you provide just power, you plug it into the wall, and then it synchronizes every speaker that you have wirelessly. So if you have 30 speakers in the house, they could all be playing the same song exactly in sync, or they could be playing 30 different songs, depending on your desire, or you can group different things together. So that was the original foundational work, the IP that went into creating multi-room audio as we know it today, was what was created. And again, I wasn't around for that period of time, but really that set up, whole home audio, a wireless whole home audio that you see today, even beyond Sonos, right? In all forms.
Jeff, what EDA software does Sonos use?
We use Cadence for all of the circuit design.
Mm-hmm.
All of the places I've been have all used different ones. So.
Right.
Do you have a favorite?
Let's see. So I personally did the most design using Mentor Graphics. That was when I was at Draper, when I was doing the most design myself. At Sonos, I didn't actually do any of the circuit design myself. So I'm not as familiar with Cadence. And then back at Radio Astronomy Lab, we were using PCAD, which Altium is Altium, right?
Became Altium.
Altium.
Yeah. Cool. So I have a question. You hinted at this, but it wasn't quite clear. Do you enjoy being an engineer?
I love it.
No, I'm just kidding. That was totally obvious.
Didn't come through.
No, it came through. It came through. Yeah, you do love it.
I love it. It's when I was at Draper, I loved every day of what I did. And it was the engineering, the problem solving, the product development side of things. But as you can see around me, I'm a musician too. And I love music, and I love everything about that side of creativity. And I never thought I could fuse the two worlds together.
Mm.
But at Sonos, I get to fuse those worlds together, which is, I feel very privileged, to be honest, that I have that in my life.
Now, Sonos, it seemed like they took a bit of a risk. They brought you in as a product leader, and you had pretty much zero experience in consumer electronics.
That's right. That was quite the interview process.
Wow.
That took about 26 hours of interviewing to convince them. But yes, yeah. And what was more fascinating, when you sit down, I never forget sitting down in Santa Barbara with the design lead, right? The industrial design lead. And the first question she asked was, well, let's see your portfolio. Let's see an example of some products that you've developed. And I said, well, I can't talk about anything I've worked on. So then it was, okay, how do I convince this person that I can translate those skills into this domain?
Wow. And
so I then did that. And some of it took second interviews, some of it took an interview over a drink or two that I didn't know was an interview, but it was really an interview to convince them that I could translate those same skills at Draper: attention to detail, planning, testing, designing, analysis, same stuff. Like everything I described for Sonos, except for making sound, went into everything at Draper. It was all the same stuff. I just had to, convince them that, yeah, it all applies. Give me a shot.
That's amazing. That's amazing.
It was what a great opportunity. Again, I feel very, very privileged to have a foundation like that. And frankly, I see there was so much talent there at both places. And if in your careers you have the opportunity to spend time in a domain that is, like in that example, it was doing work for my country, doing work in a variety of different segments that was nonprofit, but really just pure R&D. this great experience and foundational for everything that I brought over to the consumer world, right? And then so if you have the opportunity to try different things, it's great. And I would just say that make sure, like, when you do that, spend some time in there, right?
Okay.
I'm not someone that jumps around a lot, and a lot of people they move around every couple of years. I get very attached to the people. You know, one of the secrets, you know, about great product development is the human beings. It's what can make a product great. It's also the greatest challenge. How do you get this group of people that come from a variety of backgrounds to work together, and each of them is, again, pulling at a different tension, fighting for their discipline, to come together, work together, and deliver something great. So if you can be good at the human side of things, that'll get you very far as well. So don't discount that aspect of this. And it's often the people that get in the way more than anything else. The problems aren't necessarily that hard to solve, but you've got to understand what's motivating people, what's going on in their lives. They might have had something personal that's interfering. You got to understand all of that if you're leading a group of people, and that is so important. And really, what'll make or break a product.
So, I guess what I heard was Sonos during the interview, or after initial interview, they invited to drink with you. Is that and that was sort of like part of the interview? I thought that was sort of like things what happens in movies.
No, that's what happens.
Okay.
that's what happens. It was hey, before you leave, before you go back on fly back, back home, somebody's in town. He wants to, he interviewed you before, but he happens to be in Santa Barbara. Can you meet him for a drink? I was like, yeah, no problem. So I'm going there. I think we're just going to relax. I'm at hour 24 of interviews is behind me. I can relax a little bit. And then he's like, all right, just asking me questions. Like, wait a second, he's interviewing me again. He's really trying to understand how someone with no acoustics experience can come in. So I had to convince him of that in an interview. And
did you ever mention your senior design project?
I don't think it came up in that context. I have talked about it since with that same person quite recently, because he actually worked at Fishman Transducers. So he developed with Larry Fishman a MIDI guitar pickup. So we were just talking about this last week, because I'm doing a project with my son right now that is MIDI related, because MIDI's great and it's timeless. So I was talking to him about that. I said, oh, check this out, this MIDI pickup that he developed with Larry Fishman. So,
oh, nice. That's a tough problem.
It is a very tough problem.
Great.
So it came full circle.
It came full circle. Exactly.
Awesome.
I'm telling you, the stuff you're learning today. I was talking to Professor Souls about the realization that, you mean I just have to read this data sheet and all the app notes, and I know how to use this part, and that's it. Read, but you got to read the whole thing. Don't skip, that paragraph you think is irrelevant, because it'll be the one that you're debugging for hours, and you go, oh, wait a second, I should have read that piece of the data sheet. Read the data sheets front to back. Read all the app notes. Read all the errata, and then if something's still not working right, it could be wrong, right? And we fix parts all the time.
We have found that. Like, oh.
But it's the same stuff that you're learning now, and it just scales up. It just scales up from here.
So I'd like to ask Shira and Chuck just to say a couple things about their role in the team, because we've got a bit of a dream team here, and I'd like you to meet them. And we are, some students are leaving, and of course it's 5:23 in Miami, so that does make sense. But before
Baird, I just wanted to say I had to go, and I just wanted to say, Jeff, thank you very much, for spending time with us. Fabulous career. Congratulations.
Thank you. My pleasure.
You're making us so proud.
Thank you so much. And I did mean it that these are my two favorite professors, right? So anytime you want me to talk, how could I ever say no?
Thank you, and all the best.
Thank you.